Today we're going to learn about linear equations in two variables. You will learn how to graph ordered pairs, determine if an ordered pair is a solution to a linear equation, and find the missing value in ordered pairs. To begin, let's look at this graph. It shows Super Bowl average viewership from 1967 to 2010. Often in statistics, we take data like this and we fit a line to the data, our best estimate of a straight line, kind of the average of the data, so to speak, so that we can look at trends in the data or relationships among variables in the data. This straight line shows that across time, viewership increased for the Super Bowl. We might also want to look at 10-year intervals. The lines that I've shown now show the 10-year growth in average viewership across just that 10-year interval. So from 1970 to 1980, you can see that the line is quite steep. Viewership increased quite a bit in that decade. From 1980 to 1990, the line is less steep, while viewership still increased. It didn't increase quite as much as it did in the previous decade. We use pictures like this frequently in statistics to determine the trends and the relationships between variables, and you're going to start learning how to create linear equations to estimate data like this. So to start with, let's do some vocabulary. The rectangular or Cartesian coordinate system is this XY graph that shows two-dimensional space. You might know the name Descartes. He was a cartographer. He helped develop maps in two dimensions, and hence the Cartesian coordinate system is named after Descartes. The x-axis is where y is equal to 0. It's the horizontal axis, or horizon might help you make an association. Notice that if we draw that H and we add a line, we can get something that looks kind of like an X. That's an association that might help you remember that the x-axis is the horizontal axis. The y-axis is where x is equal to 0. It's the vertical axis. And if you look at that V and draw a tail on it, you've got a Y. That might help you remember the association that vertical is the Y-axis. The origin is the place where the X and Y axes cross. It's the place at 0 in X and 0 in Y. And finally, we label the quadrants in the Cartesian coordinate system. We start with the top right quadrant where both X and Y are positive, and we move counterclockwise. Quadrant 2 is where X is negative and Y is positive. Quadrant 3 is where both X and Y are negative. And quadrant 4 is where X is positive and Y is negative. These are good labels to know for the next test. We can graph ordered pairs. The numbers are in the order of X, Y, means we move in the X direction the number that the first number indicates. We move in the Y direction the amount that the second number indicates. So the first ordered pair is 0, 0. We've already learned that at the origin. The second ordered pair is the point 1, 3. That means we move 1 in the X direction and 3 in the Y direction. The next ordered pair is the point 3, 3. That means we move 3 in the X direction and 3 in the Y direction. The next ordered pair is -2, -3. That means we move -2 in the X direction, or 2 in the negative X direction, and 3 in the negative Y direction. There's the point -2, -3. The next ordered pair is -1, -2. That means we move 1 in the negative X direction and 2 in the negative Y direction. There's the point -1, -2. The next point has decimals and fractions. We can use decimals and fractions to graph an ordered pair. In this one we would move 4½ in the X direction and 1/3 in the negative Y direction. There's the point, 4.5 and -1/3. Point number 7 is the point -3, 0. That means we move 3 in the negative X direction and we don't move anywhere in Y. And finally, the last point is 0, -3. That means we don't move at all in the X direction, but we move 3 in the negative Y direction. Here's some more ordered pairs. Pause the video, graph the ordered pairs, and then check your work. here's the ordered pairs that match the points that you just graphed. Check your work, make sure you got them all correct. You can pause the video if you need more time. A linear equation in two variables has several forms. One of the forms is called standard form. It's in the form ax plus by is equal to c. Standard form has both x and y on the left side of the equation. The x term is positive. That means a is greater than or equal to 0. And the x term is usually written first. And the standard form of the equation has no fractions. So here's some examples of standard form equations. 3x plus 4y is equal to 9. Both x and y on the left. X is positive, 3 is positive, and there's no fractions. X minus y is equal to 0. Both x and y are on the left. The x term is positive, and there are no fractions. X plus 2y is equal to 8. Both x and y are on the left. X is positive, and there are no fractions. And 5x minus 5y is equal to 1. The x and y terms are on the left. The x term is positive, and there are no fractions. Here's some examples of linear equations that are not written in standard form. Y is equal to negative 3x plus 2. The x term is not on the left side of the equation. 3y minus 4x is equal to 12. Not only is the x term negative, it's not written first. Y is equal to 1/2 x minus 1. Here the x term is on the right side of the equal sign, and there's fractions in the equation. And finally, 3x plus 1/2 y is equal to 5. While x and y terms are both written on the left and the x term is positive, there's fractions in this equation. So these last four are examples of linear equations that are not written in standard form. You might recall from our last chapter, a linear equation in one variable looks something like this. X minus 2 is equal to 1. That equation only has one variable, x. And if you add 2 to both sides, you get the solution, x is equal to 3. A linear equation in two variables has both x and y. So an equation like y is equal to 4x plus 5 is a linear equation in two variables. Solutions will take the form of a point, not something that looks like just x equals 3, but the ordered pair 2, 13, where x is 2 and y is 13, or the ordered pair 3, 17, where x is 3 and y is 17, and so on. So one question you might ask is, are the ordered pairs solutions to the linear equation? So if the linear equation is 2x plus 3y is equal to 12, how would we determine if the ordered pair 3, 2 is a solution to the linear equation? Well, we would plug x is equal to 3 in for x and y is equal to 2 in for y and see if we have a true statement. So remember that x comes first, y is second. I've plugged in this equation, I've plugged x is equal to 3 and y is equal to 2. That means we'll have 2 times 3 plus 3 times, instead of y I've written 2, is equal to 12. And now do the math. We end up with 6 plus 6 is equal to 12. That's a true statement. So the ordered pair 3, 2 is a solution to the linear equation. The next ordered pair is 0, 4. X is 0, y is 4. And when I plug those values in for x and y in the equation 2x plus 3y equals 12 and do the math, I get 0 plus 12 is equal to 12. That's a true statement. That means that the ordered pair 0, 4 is a solution to the linear equation. The next ordered pair is -2, -1. So if I plug -2 in for x and -1 in for y into 2x plus 3y is equal to 12, and do the math, I have -4 plus a -3, that's -7. It's not equal to -12. It's not equal to 12. So -2, -1 is not a solution to the linear equation. Let's try the next one. Negative 12 and 12. I plug negative 12 in for x and positive 12 in for y. When I do the math, I have negative 24 plus 36 is equal to 12. That's a true statement. The ordered pair negative 12, 12 is a solution to the linear equation. One way to check your work is to graph the points and see if the resulting line to connect the points is linear. So first I'll graph the point 3, 2. There it is. Next I'll graph the point 0, 4. There it is. Let's go ahead and graph negative 2, negative 1, and finally negative 12, 12. You can see we can draw a line between the 3 points that were solutions to the linear equation and the point negative 2, negative 1 that was not a solution to the linear equation doesn't fall on that straight line. Here's another linear equation. X minus 3y is equal to 1. Plug in the 5 points that are shown and determine which ones are solutions to the linear equation. Pause the video while you're plugging them in and then check your work. Okay, to check our work, we can plug x equals 3, y equals 2/3 into x minus 3y is equal to 1. Do the math. You get 3 minus 2 is equal to 1, a true statement. That first point is the solution. For the point 7, 2, plug it in and you get 7 minus 6 is equal to 1. That's a true statement. So the ordered pair 7, 2 is a solution to the linear equation. Next ordered pair, 3, 1. Plug that in, you get 3 minus 3, well that's not equal to 1. So the ordered pair 3, 1 is not a solution to the linear equation. Next point, x is equal to 1, y is equal to 0. Plug that in, you get 1 minus 0. That's equal to 1, a true statement. The ordered pair 1, 0 is a solution to the linear equation. Finally, the last point, negative 2, negative 1. When you plug that in, you get negative 2 minus a minus 3, which is 1. That's a true statement, so that last point is a solution to the linear equation. Pause the video and graph those points. Show yourself that they form a line when you graph the blue points, and that the point 3, 1 will be off the line. Here they are. Here's the point 3 and 2/3. The ordered pair 7, 2. The ordered pair 3, 1. That was the one that wasn't on the line or wasn't a solution to the linear equation. Here's the point 1, 0. And finally, negative 2, negative 1. If we draw a line between the pairs that were solutions to the linear equation, we do have a straight line. And you'll notice that the point 3, 1 falls slightly above that line. Here's another task. If we have the linear equation y is equal to 4x minus 6, we need to find out what the missing value is in each of these ordered pairs. In the first one, x is equal to 4, so I'll plug x is equal to 4 into the linear equation. I'll have y is equal to 4 times, instead of x, I'm going to write 4 minus 6. When you do the math, that's 16 minus 6, which is equal to 10. So y is equal to 10. Next ordered pair, we're given the value of y is negative 10. So if we plug negative 10 in for y and then solve for x, we're going to add 6 to both sides. That means we'll have negative 4 is equal to 4x. Divide both sides by 4, we get x is equal to negative 1. The value of negative 1 is the value for x. Next ordered pair, we're given x is equal to 0. If we plug x is equal to 0 into the equation y is equal to 4x minus 6, we'll have 4 times 0, that's 0. So negative 6 is equal to negative 6, which means that y is equal to negative 6. The last one, we have y is equal to 0. So we plug in y equals 0 to the linear equation. 0 is equal to 4x minus 6. Solve for x. That means we're going to add 6 to both sides and then divide both sides by 4. We get x is equal to 6 over 4, which is the same thing as 3 over 2, or 3/2. Again, you can check your points. Pause the video while you graph the points and convince yourself that those points, those ordered pairs, form a straight line. Let's graph them. Here's the point 4, 10. Here's the ordered pair -1, -10. Here's the ordered pair 0, -6. And finally, 3/2, 0. As you can see, those points form a straight line. They are all solutions to the linear equation y is equal to 4x minus 6. We can also complete a table of values, just like we did the last one. So if x is equal to 10, we can plug that into the equation x minus 2y is equal to 8. We'll have 10 minus 2y is equal to 8, or when we solve for y, we'll get y is equal to 1. And I can write the ordered pair 10, 1. Go ahead and do the same thing for the rest of the values that are shown in that table, and then check your work. Pause the video while you're doing that. Okay, let's check your work. First, we've got x is equal to 2. I plug that into the equation. 2x minus 2y is equal to 8, so I'll have 2 minus 2y is equal to 8. When I solve for y, I get -3. So y is equal to -3. We've got the ordered pair 2, -3. The next value we're given is x is equal to 0. When I plug that into the equation, I have 0 minus 2y is equal to 8. When I solve for y, I get y is equal to -4. So the ordered pair is 0, -4. The next value I'm given is y is equal to 0. When I plug y is equal to 0 into the equation, I have x minus 2 times 0 is equal to 8. Well, -2 times 0 is 0, so x is equal to 8. I can write the ordered pair 8, 0. Finally, the last one, y is equal to -2. When I plug that into the equation and solve for x, I get x is equal to 4. I can write the ordered pair 4, -2. Again, try graphing those ordered pairs and make sure you did your math right. Make sure that they all fall on a straight line in the graph. Pause the video while you're graphing the points. Here's where the points are. When x is 10, y is 1. When x is 2, y is -3. When x is 0, y is -4. When x is 8, y is 0. And when x is 4, y is -2. You can see those points fall on a straight line. Those points are all solutions to the linear equation x minus 2y is equal to 8. Here's another table of values with the equation x is equal to 5. That looks a little strange because there's not a y, but we could rewrite this equation as x plus 0y is equal to 5. Go ahead and pause the video. Find the values for x when y is -2, 0, and 5, and write the values as ordered pairs. When y is -2, here's the equation. X plus 0 times -2 is equal to 5, or x is equal to 5. I can write the ordered pair 5, -2. When y is equal to 0, we have x is equal to 5. So we have the ordered pair 5, 0. When y is equal to 5, we have x is equal to 5. So we have the point, the ordered pair 5, 5. Notice that we had the equation x is equal to 5. That meant in every single ordered pair, x is equal to 5. No matter what value of y, x is equal to 5. Pause the video while you graph those ordered pairs. Notice that when we graph the point 5, -2, 5, 0, and 5, 5, we have a straight line. It's a vertical line, and at every point on that line, x is equal to 5. Here's an application of linear equations. The table shows the rate in percent of which two-year college students completed a degree within 3 years. Think about what the ordered pair 2007, 26.9 means. Pause the video while you write down the meaning. The point 2007, 26.9 means that in the year 2007, 26.9% of two-year college students completed a degree within 3 years. Now, write the ordered pairs and graph them. Here's the ordered pairs: 2002, 31.6, 2003, 30.1, 2004, 29.0, 2005, 27.5, 2006, 26.6, and 2007, 26.9. Pause the video here and see if you can create a graph of those ordered pairs. Okay, here's a graph. The first thing to do is figure out what the x and y scales will look like. I'm going to graph every other square as a year. So you can see that I've got 2002 through 2007 on the x-axis. The x values were the years. I label that axis year. For the y-axis, I've got to deal with those percents. I'm going to label them 26 from the bottom up to 31 at the top. You might have labeled yours a bit differently if you did them by yourself. And I need to label the axis the percent completing college. Now I can graph the points. For 2002, I go up to 31.6. For 2003, I go up to 30.1. For 2004, I go up to 29. For 2005, I go up to 27.5. For 2006, I go up to 26.6. And for 2007, I go up to 26.9. Those ordered pairs don't all fall on a straight line, but like we did in the football example at the beginning of this lesson, I can draw a straight line that estimates the value of those points. So here I've drawn a line that the distance from the line is going to be about the same on one side as it is on the other. The line is an estimate of the points. Now, describe the pattern. What's happening to graduation rates? Pause the video while you write that down. What's happening to graduation rates? The percent of students completing college within 3 years is decreasing across time. That means in 2007 there were fewer students, or a smaller percentage of students, completing college within 3 years than there was in 2002. Lines are often used to model real-world data. When this is the case, the steepness or slope of a line always has a contextual meaning related to the change in the y variable compared to the change in the x variable. Let's look at one more example. The graph below depicts a linear relationship. Determine the cost of a speeding ticket if you're traveling 40 miles per hour over the posted speed limit. Pause the video while you see if you can figure out what the cost of the speeding ticket would be if you're traveling 40 miles per hour over the posted speed limit. Let's extend the line and figure out the increases in x and increases in y with each of those points. Notice that if we move from one point to the next in x, we have a 10 mile per hour increase between 10 and 20 and 30. In the y direction, we move from 50 to 150. That's a $100 increase. And then from 150 to 250, that's another $100 increase. So if we extend the line and graph the point for 40 miles per hour, we can see that that's 10 miles per hour increase above 30, which means that we have a $100 increase in y. That would be the point 40 comma, 350. Pause the video and see if you can find the cost of the ticket when we have 50 miles over the posted speed limit. Okay, we don't have enough room on the graph to go there, but you should have found the point when we are 50 miles per hour over the posted speed limit. The ticket is $450. This is an example of a linear relationship between the miles per hour over the posted speed limit and the cost of the speeding ticket. That ends your lesson for today. You're able to do the homework now for section 3.1.